I'll be talking about, I added foundation models to the title. So foundation models, generative models, and inverse problems. I want to emphasize, first of all, that this work is 100% possible because of all the great students that we've had here in UT throughout the years that I'm listing here. Also, many wonderful collaborators in many universities, including the Datacomp team that I will explicitly mention, which is a very large team from 34 students and colleagues around many universities and industry. So, first I want to talk a little bit about foundation models and how I think they're shaping research in AI in ways that I think we cannot ignore, even if we want to. Then I will tell you how this is informing the solution of inverse problems, the theory of compressed sensing, and kind of the things that I have been interested in for a long time. So when people say, what is a foundation model, what everybody knows is ChatGPT or Claude. These are text autoregressive models. And by the way, please do jump in at any point to have more fun and have an interactive conversation. So the first thing I want to say is that a foundation model, like this is a text autoregressive model, of course, but there are many models that are foundational, as I will explain, that are not text models. And also there are models that are foundational that are not generative models, okay? So I want to clarify this because I think everything that's going to be built will be built on foundation models. So I want to clarify these points. So StyleGAN 2 and DALI 2 and Stable Diffusion are all generative models of images. They're text conditional models. You can say, give me an image of a cat or give me an image of a cat dancing in the style of Picasso and so on. And, this is a GAN and these are diffusions. And I will explain why I consider them foundational models or foundation models in a minute. But these are generating images. CLIP is a model that doesn't generate anything. It is basically a model that takes some text and produces a vector, and then takes an image and produces a vector. And then it just produces representations of both images and text in the same space. So it's a multimodal model. And as I will explain, it is extremely important as a foundation model because you can build many things on top of it. I will clarify again why. And then there's models like Whisper, which is for audio to, speech to text. And these amazing models in vision that can segment anything, which is an incredible new capability. Some models in this list, as I said, are generative and some are classifiers. And another key parameter is that they're trained at the billion scale versus million scale. For the ImageNet, I used to consider ImageNet, a big data set that I could hardly train models in academia. But right now, it's considered a small data set, whereas all these models are built at a different scale. And what seems to be happening, I think, in AI is that as you're getting to this new scale of billions, there is these phase transitions that are enabling new capabilities that are, I think, completely changing the way we would be building models. Now, what makes something a foundation model, in my opinion, and I think also in the definition that they gave, is that you can build on top of it, okay? So a foundation model is something that is trained to do one job, like, for example, predict the next word. But now you can use it to make a sentiment detector. Like GPT was not trained to be a sentiment detector, right? It was similarly, you can have a model that's generating images and build on top of it and build a model that can fill in missing pixels, okay? So the model doesn't know how to do that. How we do it with a model is a key part of the algorithmic innovation. And the algorithmic innovations that are happening today range from obvious things like prompting techniques to fine-tuning or LoRa or other parameter-efficient fine-tuning. There's a whole huge algorithmic optimization space on how you fine-tune a foundation model to teach it a new trick, as I will be saying. But there's also other less obvious ways that a foundation model can be used to build. And one of them is through filtering. So you can use it as a way to clean up a data set, to select a subset of a data set. And this has been key for the existence of some of the open foundation models. So there's an extremely interesting story I want to tell you here, that filtering has been the reason, for example, why we have stable diffusion. Stable diffusion exists today because OpenAI released CLIP, and Lion was created using CLIP as a filtering mechanism, and then OpenClip was trained on top of Lion. So there's a bootstrapping mechanism where there's data sets, then there's foundation models used as filters, then there's new foundation models used on top of the new data sets. And then finally, another thing that I think we're seeing more and more now is you can use the foundation models to do synthetic data set generation or synthetic data set augmentation. For example, you could take images and caption them synthetically using GPT-4V and create a better image caption data set. And I think this has been a key in the next generation of video and image generative models. So I believe, by the way, I'll make this prediction just for fun. I believe that almost all of AI in the future will be building on top of foundation models. So almost never will be the case that something will be trained from scratch. So this is an extremely important area, of course. Now, another thing is that foundation models are closed, and there's different levels of being closed. For example, the thing is you give you API access. Or, of course, I could not even give you API access, just keep it internal in a company, but then I could give you API access, or I could give you the model weights. And many companies are now releasing these foundational model weights, which is great, but almost nobody is releasing data sets. And I think the data set is something you would need if you're going to fine tune or distill or try to teach this model new tricks. You actually need the data set to perform many of those steps here. So one of the things that we have identified in our institute is that we need large open multimodal data sets and model weights. And I think this is key to have a competitive AI ecosystem, because I'm worried that one of the biggest risks in AI is that if only very few companies are controlling the data sets and the foundation models and everybody else is building on top of those foundation models, then you have a unique problem of monopolies being formed, and nobody else can innovate. So in this NSF institute that we have, the Institute for the Foundations of Machine Learning, two huge initiatives that we have. One of them is on creating new foundation models, and creating the data sets to create new foundation models is probably the most challenging part, actually. And the second part of my talk, and also like a big part of our institute, is, okay, now that you have a foundation model, how do you teach it a new trick, as I say? So I will explain what that means. Solve a new problem or teach it a new concept, like teach it, for example, to generate images of me. Like, Stable Diffusion doesn't know how to generate me. I'm not that famous, unfortunately, but there's ways that we can teach the model to generate me, or to generate specific, consistent personas throughout time, and so on. Also, obviously, accelerate the models and so on. So this is kind of the high-level two views of my talk. And another thing that I want to say is, I believe that, especially when we talk about new foundation models, most of the innovation is happening in the curation or the creation of the data sets, not so much on the algorithms to train them or the neural network architectures. It seems that the architectures have very few choices that are all standardized now, unless, of course, some new architecture makes a breakthrough. But and there are some research directions that are trying to convince that, but most of the effort seems to be going on creating the data sets. And creating the data sets has algorithmic problems of its own, as I will try to explain. So I will be telling you the first part of my talk, how we created DataComp, which is a very large multimodal data set, which was built along the previous very large multimodal data set called Lion. And the second part of my talk will be teaching foundation models new tricks, specifically how to solve inverse problems using a pre-trained Stable Diffusion. Then I will talk a little bit about this idea that we have that's called ambient diffusion, which is how do you train diffusion models if the only data you have is corrupted. And then maybe, if I have time, how you can teach a foundation model new concepts, like, for example, to generate images of your dog and so on. So the first thing is there's a trend right now on multimodal models. I think people already know GPT-4V is a model now that can take in the prompt text. Like here's an example. It says, look at this CT scan of lungs in the image below and tell me what's wrong. And then you can upload an image. And GPT-4V starts producing some diagnosis here. It says there appears to be multiple areas of consolidation and ground glass opacities, blah, blah, blah. So I don't know what that means. I showed it to some doctor friends and they said this is wrong. But it is actually, plausible. So you shouldn't quite fire all the doctors and rely on GPT-4V. But, as the model is getting better, it will perhaps be able to give reasonable diagnosis here. But it's definitely having the ability to see images and integrate them in the flow. So what we've been trying to do is create large open multimodal data sets. And the starting point is this Lion data set. The Lion dataset is 5 billion image caption pairs created from the internet. So I want to tell you how this thing is created, because this was also the starting point for our effort, DataComp. So the first thing is you start with something called Common Crawl. Common Crawl is a scrape of the internet. Okay, so any image you may have uploaded on the internet, it's sitting on some HTML somewhere. So this thing just takes all this scraped HTML and it looks at image tags like JPEG links and so on. And then it needs text also. And the text is the alt text that the image caption has. There's an option in HTML to put an alternative text for every image. So people just started with Common Crawl and they took every link that's an image and kept the corresponding text. And the problem with this thing is that most of the images on the internet, the alt text is not a very good description of the image. The example I say is, if you take a picture of your dog and you put it on Instagram, you're not going to say an image of a Labrador running in the park. You're going to say, this is Bob, isn't he cute, lol, 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 right? So that text is not going to be a very good description of the image. So dataset creation at internet scale, at the billion scale, is actually a dataset filtration problem. You want to start with hundreds of billions of images and text that are not well suited, and you want to pick the subset where the images actually describe, the text actually describes the image. And how do you do that, or how did Lion do that? The first answer is they used another foundation model. So they used CLIP. So CLIP was released gladly by OpenAI, only the weights. The data set where CLIP was trained, we don't know. But using CLIP, you can filter Common Crawl and create a new data set. And that was basically Lion. And then Lion, the data set, was used to train Stable Diffusion, which is the best open generative model for images, and OpenClip, which is now the best retrieval and multimodal foundation model we have. And you see the bootstrapping effect. The reason OpenClip exists is because Lion exists, and the reason Lion exists is because Clip exists, right? So there is this very interesting bootstrapping going on. So Lion has been an extremely impactful project. It is used by countless companies, startups, research labs, and so on. And it also won the NeurIPS 2022 Best Paper Award. So our effort is called DataComp, and it is basically Lion 2.0. It was the next generation of Lion. We wanted to fix several of the problems of Lion, and you can see that it's a very large collaboration of 34 co-authors from University of Washington, Apple, Tel Aviv, and so on. So the University of Texas is here, and our institute is here. So DataComp is the next version of Lion. So there were several things where we innovated on, and I want to tell you about them. First of all, it's the largest public multimodal data set that exists today. It's at 13 billion image caption pairs, so it's larger. And we thought that instead of making it only a data set, we will make it a competition. So I will explain how there is this data-centric view, which completely flips the previous machine learning view on its head. I will explain how. The basic idea is that what we created is a pool of billions of image caption pairs that's already pre-filtered in various ways. But when somebody participates in DataComp, they are to select a subset out of this pool. And then once they select a subset, that's the task, select a subset of high quality. And then we provide the fixed training code and a fixed evaluation code. So you get a clip model from your selection. And then we have a whole evaluation benchmark, like 38 benchmarks actually, including ImageNet zero shot. And we tell you how good your filtration mechanism is. So it's a competition for dataset filtration methods, which are performed by training other filtration models. And other things we did is we also detected and blurred faces because there was a lot of personally identifying information on Lion because it was, just scraped from the internet, which was making many companies not being able to use it for legal reasons. There was also NSFW, violence, terrible things on the internet. So we filtered a lot of the NSFW content that was in Lion to make DataComp is a much cleaner data set. And the things we realized early on is, okay, let's redo the Lion 5B, but in a flexible and reusable way. And we're not only publishing the data set, but we're publishing the entire tooling around it. So tooling means things that are software engineering based, like how do you do deduplication at the 13 billion scale? How do you do filtering? How do you do the data loaders so that they're fast? Things that we thought were easy until we actually tried to do them, and we realized that it's an immense effort. But once you do it once and you make the code open source, it's very easy for other people to use these tools for their own dataset curation efforts. And the next idea, as I said, is to make it a benchmark. So it's actually a competition, and then do workshops, in ICML and so on, where people are coming in and discussing how well their filtering algorithm did on a fixed pipeline. And the goal was, to make collaborative data-centric research a first-class citizen in AI, similar to what we all know as model-centric research. I just like to, give that slide. So traditional ML says the data set is fixed. For example, ImageNet, right? We all know MNIST, ImageNet. And then you come up with a method, I come up with a method, everybody comes up with a method, and we report how well we did on ImageNet. DataComp says the model training code is fixed. The model is a VIT. The training code is fixed. The learning rate is fixed. Everything is fixed. But you just iterate on the subset of the training data, and now you're evaluated on how good your data selection process is. So this is what's called data-centric AI. And more concretely, DataComp provides a few different pools. It starts from 12 million image caption pairs, so 12 ImageNets, which is pretty manageable even for a small academic lab with one good GPU or 4 GPUs. They can train models at this scale, and goes up to 13 billion image caption pairs. And then, as I said, there was a big effort on safety, so toxic content, filtering, face blurring, and data poisoning protection. And then we standardized the training code for clip models. So everything there is fixed. You just say model.train. And then you say model.evaluate. And the evaluation is automatically done on 38 downstream benchmarks that have a very wide range of evaluations, including on diversity-related AI problems. And the participants, what they have to submit is basically a subset of the pool and how they filtered it. So they say, okay, out of the 13 billion, I selected 1 billion. And here's the list, image 7, image 21, image 37, and so on. And one thing that I want to emphasize here is, since there is a 13 billion pool, one thing you can do is filter nothing, keep the whole pool. If you do that, you're going to run one gradient. We're going to see one step on each of the images. So 13 billion images will be seen exactly once. If you instead filter this and your data set is 1 billion image caption pairs, then every image you will be see 13 times, right? So we fix the total compute, which is exactly proportional to the cost you would be paying to train these models on your AWS bill, your compute bill. So the short answer is perhaps you should just keep all the data. Maybe that performs the best. And the answer is absolutely not. If you do that, it's going to perform very poorly. And that's exactly why this is an important problem to consider. Another option we have here is that you can bring in a new data source, either real or synthetic. So you can also train on new image caption pairs, and you can still run the evaluation. And that's also a different track that we support. We call it Bring Your Own Data. And this is primarily to facilitate research on synthetic data sets. So the impact of the competition, probably the most significant impact has been not the competition itself, but rather one of the data sets. So we released Datacomp 1B, which is a very highly filtered, high quality data set. And then using the Datacomp 1B, we were able to get clip models like this one that has 79% ImageNet accuracy, which outperforms the model trained by OpenAI and outperforms a model trained on Lion 5B. And that's also important, that this is a 5B model, whereas our data set here was 1B. So by using much less training data, much less compute, we got like a very, very good data set, Datacomp 1B, which is widely used now, as far as we know, by many companies, including Anthropic, Apple, and Meta, and many others. And using this data set, we also trained OpenClip, which is, I think, one of the best, or if not the best, multimodal model that exists today. That I see, for example, it has 50,000 downloads per day for people using OpenClip. And another thing is Datacomp is used in Stable Diffusion, and I think it's also used in many other open models. And it's an ongoing competition. You can see here, if you go on Datacomp AI, you can see we have different tracks for small pool, medium pool, all the way to very large. And you can see people participating with different algorithms. And here we have our ImageNet accuracy and the average performance and so on. So we're trying to create a community of people investigating data curation methods here. And I think it will be a very important part of the AI ecosystem. And we're trying to make it a first-class citizen in research, not like the ugly thing that the undergrads do as a class project, which was what data cleaning used to be considered. Right? So that's kind of the first part of my talk here. So then I can take some questions if anybody wants to ask anything about Datacomp at this point, before I move into more algorithmic ideas. If anybody wants to ask anything.
Sure, I've got a question. Really excellent. I appreciate you taking the time. I'm coming from a lot of biomedical algorithm development. And of course, we deal with a lot of bias, right? The training sets for images are biased, causes some trouble when it's, medical records, then you're giving people harmful medical advice based on their skin color and that kind of thing. When you're talking about being able to synthesize data, my mind goes to groups trying to use this to augment, excuse me, medical advice. I assume you've spent some time interacting with people at that frontier. Do you have thoughts you can share about sort of concerns and benefits of synthesizing human biomedical data in a context like this?
Yes. So on synthetic data, I think it's an extremely important frontier, as you said. It's the reason I believe synthetic data set creation may be possible now to a different level of performance compared to before is because we have now these foundation models like Stable Diffusion that have been trained on such a huge, diverse data set. So they not only are trained on generating, dogs or human faces, but they have been trained on the whole internet. And we think that with very little additional specialization, they can produce synthetic MRI scans or synthetic, CT images, or depending on the domain, of course. I have seen people apply to histology, to MRI, to CT, and I think that the ability of these models to generalize in other domains, this is also, remarkably shown in GPT, right? GPT you can ask GPT to create, to write a rap song about some Shakespeare novel, and it will remarkably be able to combine existing patterns in very novel ways. And I think this fact can also happen in images. And as far as I know, it hasn't been fully demonstrated, but I believe that it was possible now for the first time because we have these amazing generative models like Stable Diffusion, SDXL, that are open, the data sets are open, and I think they will be able to generalize in other domains. We are working on it for MRI, and I think there's a lot of work to be done there for different domains. Yeah. So maybe I'll move on then, and we can take all the questions in the end, unless somebody wants to ask another question about datacom. Okay. So let's move on. So the second part of the talk is, okay, you have created those data sets and those foundation models. Now you want to teach existing foundation models new tricks. So I'll spend a little bit of time on the first trick, which is in painting, but using stable diffusion. So this is based on this paper that's called PSLD, solving linear inverse problems, provably by posterior sampling with latent diffusion models, that was in EURIPS this year. So the foundation model we start with is called stable diffusion. Now, stable diffusion is a latent, let's see what it says here, it's a latent diffusion model. So the first thing it does is it takes an image X and it passes, it has an autoencoder, basically, an encoder and a decoder. So it takes the image and projects it or embeds it into a much lower dimensional space that's called Z. And, you know, these can be 1,000 by 1,000 images, but these can be 64 by 64 by 8 or something, like very much smaller. Think of them as low resolution images, essentially, but with a lot of channels. And then the diffusion process, the denoising, if you're familiar with how diffusions work, the whole diffusion is happening in this much lower dimensional space. Finally, what is produced in the end is some Z final, and this Z final is decoded back to a pixel, an image in the high dimensional pixel space. So these are called latent diffusion models. And the reason people went to latent diffusion models as opposed to pixel diffusion models, which was what was previously done, is because it is they're much faster. A diffusion model is a denoiser, which is a neural network that goes from an image to an image. So if the images are 1,000 by 1,000 pixels, these were huge networks. Whereas all the diffusion denoisers are trained now on a much lower resolution, which accelerates and also makes it much more memory efficient compared to pixel space. So stable diffusion and its most recent variants, the most recent one, I believe, is something called SDXL. Like that's one of the best foundational models that exist right now. They are all excellent generators of images. So you can say, give me an image of a dog dancing around and so on, and it will produce an image. And they were trained initially on Line 5B, and some of them are now using datacomp, as I said. And they generate great images, but now we don't want to generate images. We want to solve inverse problems like in painting or compressed sensing or deblaring and so on. So that is kind of the problem is, okay, how do I use this whole thing, this whole box as a prior distribution to perform my in-painting problem? And just to make sure we all understand, in-painting means that, you know, I have an image, let's say X, and I'm observing this. So let's call this Y, and I'm going to be writing throughout this talk, Y is AX. So A is like a forward operator, as we say. Think of it as a matrix that if I was observing all the pixels, this would be the identity. Now these pixels are all removed. So I think of this as a matrix that is M rows. M is the number of observed pixels. And every row is a subset of the identity if I get to observe that pixel. Otherwise, I drop it, right? So this is like changing the dimension. So the problem of in-painting is I want to go from Y, which is this image with missing pixels, back to this reconstruction here, X hat, right? So this is, of course, a linear inverse problem where the forward operator A is just a subset of the identity, and it's one very, very well-studied problem. People in compressed sensing have studied this problem very well, as you know, where they were assuming X is sparse in the basis, and sometimes people assume A is Gaussian IID. This is a different forward operator, but extremely useful one. And you can see immediately the results we have here that this is the actual in-painting we have obtained with our PSLD algorithm. And this is another example. This is the input image. This is the observations Y. So you see these are missing pixels. And I just want to clarify again, in painting, you know which pixels are missing, right? So this is in painting, and this is the final result. You can call it X hat. The other thing I want to say is stable diffusion does not do that, right? So we have to use stable diffusion somehow to support this new trick. And the other thing is, of course, there is a lot of prior work on this. Okay, so I'm just explaining here, given an image with missing pixels, complete the pixels to preserve the statistics of the image. So the whole game here is, all right, you're missing these pixels, but you know something about images. So you have to fill this in. And as we said, the classical approaches were saying the image is sparse in the DCT domain, the image is sparse in the wavelet domain, and these data-driven methods say this is coming from natural images. I want to emphasize that this problem is very hard because the distribution is not faces or dogs or some narrow domain, which has been studied for a long time, but it's the Wild West. It's any image you can find on the internet. So this is a very challenging problem in painting in a very general domain. So it's, of course, a missing data problem for pixels. And here is some of the prior work, the ones we're building the most on. So as I said, this has been studied for a long time, the problem of in painting using generative priors. Specifically, we're building on this work, the DPS paper. DPS stands for Diffusion Posterior Sampling, which appeared in ICLR 2023. And before that, there's a lot of extremely important work that has informed our algorithms here. So here is the foundational new idea, the algorithmic idea here. Because latent diffusion models, okay, just to explain one thing, DPS does not work for latent diffusion models. It works for pixel diffusion models. So you can view our work as adapting this algorithm in latent diffusion models. So now I have to explain to you what is the problem with latent diffusion models. When you have an image, you pass it through an encoder and you get this latent vector ZT. And here you have a compression, right? The dimensionality of Z is significantly smaller than the dimensionality of X. So these encoders are many-to-one mappings. There are multiple images that map to the same Z. Okay. The next thing to realize is that in these latent diffusion models, the whole process of diffusion is happening in the latent space. So in the latent space, this Z may travel in some unforeseen directions depending on the observations. And that's kind of the key thing we realize we have to control here. The diffusion process is happening in this latent space. And what we realized is the problem. Okay, so let me just define the math a little bit. So X0 is this unknown image we want to reconstruct. We are assuming we're observing A times X0. A is a matrix in the simplest case for linear inverse problems. And for in painting, as we said, it is this matrix that drops some subset of the rows. And you could or not have noise in the observations. Now, to solve a linear inverse problem using a diffusion, you use the conditional reverse SDE. This is kind of the key technology that has been developed, where you say, I'm going to start with pure noise, and I'm going to be denoising it a little bit at a time, but at every step, I am also going to use Y. So as I am denoising it, I'm getting images that satisfy the measurements and also look like they have high likelihood. This is kind of the key idea of all these methods. So the conditional reverse SD has two terms here. You don't have to worry about this, all this is standard fixed things, but you need this. This is the score network. This is something that the unconditional model knows. What this ends up being is a neural network where you feed it an image XT, and what it gives you back is a denoised image, basically, or a direction, or an estimation of the noise, so that you add this to your XT and you get a slightly less noisy image. So think of this basically as a denoiser, a neural network that does denoising. But this thing is the second thing you need, and this is now a conditional, which uses Y. So this is where all the algorithmic innovation is happening. How are you going to use your measurements to use a pre-trained diffusion model to solve inverse problems? And DPS was using this method. And what we discovered in this paper is that as you're running this diffusion, you get to bad Z vectors. Okay, so I have to tell you what a bad latent vector is. So first of all, I'll show you this experimentally. So we took this image, for example, this image we found from the internet is not in the training set. And you can ask me, how do you know it's not in the training set? So the easiest way to know an image is not in the training set is take a picture with your phone, and then it's not. So basically, by the date of the image, you can be sure it's not in line. So this image, for example, and we removed some, we do some in painting. So you see we delete some pixels, and you see the previous state-of-the-art method produces, I don't know if you can see, but these are pretty bad artifacts in the face. It does pretty well on the sand. the missing sound, but it does very well, very badly on the face. And you can see another image here that produces some bad artifacts on the faces. And this is just running the previous method in the latent space, ignoring the fact that it has a latent space. So this is a naive application of the DPS method for latent models. Just to be clear, the DPS paper never proposed this. We just said the naive extension of DPS has problems. And this is kind of the key idea about what the problem is and how to fix it. So when you're training an autoencoder, this is the key thing you want. You take an X, you encode it, this is a Z, and then you decode the Z and you want to get back X hat. So if you write a loss for this, this is how you train your autoencoder, so that D of E of X minus X is minimized, right? And you minimize this loss with respect to the weights of the decoder and the encoder. But this is what we discovered matters also. So you can take a latent Z, decode it to get an image, and then re-encode that to get back to the latent vector. And the question is, is this Z the same or different than the original? So what we discovered is that there are some Z's where this happens, and there are some Z's where this doesn't happen. And when the images were looking bad, those Z's did not satisfy this property, okay? So we said, all right, not during training, I'm sorry, we're not updating the weights of the diffusion at all. During the solving of the reverse conditional SDE, as we are doing this diffusion, we are going to add this term in the reverse diffusion. So we're going to encourage the diffusion to go to Z's that satisfy this property, that they're fixed points in this reverse autoencoding condition that we wrote there. So we added this term in the diffusion, and we call this the gluing loss. So there's a few extra bells and whistles that I won't get into, but the gluing loss says that, okay, so we know that you're observing, so I'll show the main point. As you're running the diffusion, these pixels here, you are observing them, right? So at any given time during the diffusion, you can glue back the observed pixels back in the image and go back in Z and stick those in there so that it's satisfied. So the X glued is a concatenation of, this is the in-painted pixels, but for the observed pixels, you're literally replacing them. You're literally hard coding them. So in every step of this process, we are projecting basically on the set that satisfies the measurements. That's another way of thinking about it. So instead of running the diffusion using only the conditional, you also add the projection step to make sure you satisfy the measurements. So we created basically a new term loss for this that I explained, and we also added a hard satisfaction on the of the observations, and this leads to the PSLD algorithm. And then, of course, the proof, is in the pudding. You have to show that the reconstruction you get is better than the previous state of the art, both by showing examples, as you can see here, that the eyes are a little better, and here too. And then you also have to show, of course, numerical. Numerical are later. Now, the same method you can use to do deblurring, okay? So in deblurring, this is Gaussian deblurring. So the forward operator is no, and it's supposed to be a Gaussian averaging. This is the input images here, like these ones. And again, they are in the wild. This is the ground truth here. And this is the previous method DPS, and this is our method here. And you can see it's a little better. And it's also using the remarkable strength of stable diffusion, and it's able to do, deblurring of arbitrary images in all kinds of domains. This is the quantitative comparisons, where you can see here in this example, in this experiment, we are varying the percentage of dropped pixels up to 80% of the pixels are dropped randomly in this example. And you can see LPIPS is one of the perceptual distances. And here we have PSNR and SSIM. These are three different ways of measuring the quality of the in-painting. And you can see that, PSLD is performing significantly better. And we also made a web demo where somebody can upload their own image, mask whatever they want, and get the in-painting. And very recently, other groups have further extended the idea of PSLD by adding a prompt tuning idea here. Prompt tuning says we're also doing gradient descent in the text of the prompt to satisfy the measurements. And this further improves the performance. And this is a very active area of research right now. that has also a direct application to computational photography, going all the way to, you know, Magic Eraser and tools that are shipping in phones right now, right? You can mark in a phone an area and use one of those in painting techniques to fill it in. So I think these methods would be transforming the way, even in phones, people are in painting pixels, or even deblurring and so on. So there's a very short transition, I think, to go from research into product in this space. Yeah, so I just want to briefly tell you about another idea. So this idea is called ambient diffusion. So here is a problem that initially I thought was impossible. Let's imagine that you're given only corrupted images, okay? So you see these images, this is the only thing that's given to you. Let's imagine that you were born and you had only seen photographs that have a random gray square missing. And you know the corruption process, okay? So you know that what happened is there was an image and somebody randomly selected a square and removed those pixels for you. Is it possible to learn the distribution of clean images? Okay, that is the question. And the assumption is that you know the corruption process, but you don't know anything about the original distribution. And the answer is, in general, no. But under several pretty mild conditions on the corruption processes, the answer is remarkably yes. For example, even if you were observing random Gaussian projections, even if you were observing one random pixel, one pixel, that's a projection of the image, you know the weight coefficients. Then you can learn, provably, in theory, the distribution of images by observing one pixel. So in this case, I'm going to show you how you can do this when you're observing missing pixels, when your training set has random missing pixels. And these problems where you try, now I want to emphasize something here. There's one problem of reconstructing this particular person's face, right? That's an in-painting problem. But the ambient diffusion is not trying to reconstruct any one particular image. In fact, it doesn't want to reconstruct a particular image. It wants to learn the distribution of images without ever seeing a clean face, right? So you can think of it also as a privacy metric that, oh, I want to train a generative model on MRI, but the hospital doesn't want to give me MRI images, so it gives me only corrupted images. Can I still learn the distribution of clean images, right? So that's kind of one way. Or your MRI scanner may be broken and you never even get to see clean MRI images. So the theory says you observe Y is AX, A has a distribution, and you know A, right? The problem is you want to reconstruct, you want to learn P of X. You want to learn a diffusion specifically that samples from this distribution, if that is possible. And I'm going to try to tell you when it is possible, when I know it's possible, and sometimes where you can also think of cases where you can easily prove it's not possible. But it's possible for a wide range, more than I thought. So the first paper we had in this was in 17, I believe. It was called ambient GAN, and we showed that you can do this with a GAN, assuming you have an infinitely powerful discriminator, theoretically, and also practically we got some reasonable experimental results. But now diffusions are performing much better in practice, so we said, okay, how do we do it without the discriminator? So let's briefly talk about that. And we have been working on this space very actively. So when you're training a denoiser to do these diffusions, this is a denoiser, right? The denoiser is a neural network that takes an image, a noisy image xt, and T is the noise level. This is the corresponding clean image. Now, in classical diffusions, you would be forming this xt, you know, by taking the clean image and adding some noise to this image, right? That would be Gaussian. And during training, you have this, and you create this, and you just train the neural network with this loss. This is the denoising score matching objective. It's just supervised learning to make a denoiser, right? That's how you train diffusions. It's just supervised learning to get a denoiser. So now, in ambient diffusion, we would like to do the same. We would like to train H to do this. But now we have a problem, of course. We cannot do this because we don't have a clean image. What we have is Y, which is A times X0, right? So in simple words, these are all the pixels, but I'm not observing all the pixels. I'm observing half the pixels, right? That's the things. So you say, okay, I cannot train a full denoiser, but naively, I could train this. Okay, what does that mean? This is what I have, right? These are my observed pixels. So I would like to say, okay, denoiser, you are going to see an image with a missing block. You are going to produce a full image. And what I will penalize you to do is I want the observed, I will mask that, right? So I'm observing only, I'm keeping only the observed pixels. And I want you to match the observed pixels, right? So this would be a conditional denoiser that is going to try to denoise both the pixels that are observed and the pixels that are missing, okay? But then it's going to be only scored on the pixels that are observed, because it cannot be scored on the pixels that are missing because I don't have the pixels that are missing. So I could not be possibly scoring this denoiser on those pixels. Now, if you do that, you realize that the denoiser is going to learn to denoise, but ignore the missing pixels, okay? So this is what this is saying. This is the conditional expectation, but it's actually A times the conditional expectation. So this will become a good denoiser, but it will never fill in. So in pictures, if you try, it will denoise. If you're adding noise here and you ask to denoise it, it will denoise it, but it will not do anything here because it has no reason to do anything here. It will not be evaluated here, right? So that's the problem, is how on earth am I going to teach the model to fill in missing pixels when I cannot evaluate it on missing pixels? So the denoiser H in general can be arbitrarily bad in the null space directions of A, or more simple, it has no reason to fill in missing pixels because it's not part of the loss. So how do we fix this? And the idea of ambient diffusion is we're going to add additional corruptions, and we're going to test on those additional corruptions. Okay, let me explain. So this is the original image that I have in my training set, okay? Here, I remember, I never see clean images, right? I see images where 50% of the pixels are missing, so the rest are gray. This is A times xt. And one thing I can do now is I can go and create a new matrix, a hat, which is deleting additional pixels. Let's say 10% more pixels I am going to delete, and I'm going to color them green for your visual satisfaction. So you know that the green ones, I know the ground truth, but I'm just hiding them from the model. And the gray ones, I actually don't know. And now I'm going to ask the model to denoise these images. And I'm going to score it not only on the observed pixels, but also on the green pixels, okay? And the key idea is the model doesn't know which ones are the green pixels, all right? So it's like a situation where you're giving a test to your students. And if you were saying to your students, I'm not going to grade the last 5 questions, they will not answer the last 5 questions. But if you say, I'm going to only grade randomly 10% of the questions, then they have to answer all the questions because they don't know which ones are the green ones, right? So that's kind of the key idea that is used in ambient diffusion. Here is another example with a missing square. I have this image and I don't actually know what's here, so I cannot grade the model here. But what I'm going to give to the model is this image with 2 missing squares. And now the model doesn't know which one is the green square, so it has to fill in both squares. And I'm only going to put in the denoising score matching the green square because I cannot put this because I don't know what to put there, right? So this is the key idea of ambient diffusion. So a hat is this additional corruption. And now we are able to write this loss. This is the loss that's used. And I'm saying I want the denoiser. The denoiser takes the current image, the corruptions, but it's scored on slightly fewer corruptions because this I do have. And I can use it on my denoiser. So, and then we have a theorem that we can prove, and it's pretty straightforward to prove, actually. If you assume that A and A hat have a joint distribution that has a key property, for example, imagine A is just randomly flipping a coin for every pixel and keeping and deleting it with 10%, and A hat is from the observed pixels, remove 5% more. Then what you want is that the conditional expectation of this matrix to be full rank. Then you can easily prove that the unique minimizer of this loss is actually the best conditional denoiser, which actually fills in all the pixels. The intuition for this is actually, since there is non-zero chance, that the key idea for this is, okay, when the model sees these pixels are missing, can it know which ones are missing for real versus which ones it will be graded on, okay? If it cannot infer which ones it will be graded on, it will have to learn this. And it's a pretty straightforward proof. And for the model I described where I'm flipping coins, it's also obvious to prove this because there's a small but non-zero chance that nothing is deleted. So, you know, the moment you have models that are like that, it's almost trivially true to show that the minimizer is going to be to learn the correct conditional expectation. But the general condition is this, and it's something straightforward to show. I want to say something else that I think is very important on ambient diffusion. So we did the following interesting experiment. We took a small training set of faces, I think something like 100 here, and we fine-tuned stable diffusion on only those 100 faces. And after we fine-tuned it on a small data set, what happens is you see it generates images like this. And then when we go back to the training set and look at the closest image in the training set, it's identical, okay? So what has happened here is when you fine-tune stable diffusion on a data set, if it's small, especially, it will perfectly memorize the training images. So if a hospital gives you MRI images of people with cancer and says, yeah, let's make a diffusion model on that, and you just fine-tune, and it's not a very large data set, it's very likely that your model spits out actual images from real patients, which is a huge liability and problem. Instead, what we show here is we use the same training set, a small training set, but we never train with clean images. We add noise to the images, and we use ambient diffusion to fine-tune. So we call this ambient fine-tuning. So we use ambient fine-tuning to still fine-tune stable diffusion on the same data set, but using this trick of additional corruptions and so on. And now you can see that this is a generated image, and this is the closest image in the training set. So this is a test we use to see if it has memorized or not, and you can see that it has significantly mitigated the memorization when you're doing this ambient fine-tuning as opposed to normal fine-tuning. I want to emphasize that this is not a huge problem when your fine-tuning set is in the order of 10,000. Or 50,000, but if your fine-tuning set is in the order of hundreds, it's very much a problem, okay? So an ambient diffusion fine-tuning is one way that you can mitigate it. And here's another example. This is the training data that you can see is pretty severely corrupted. And these are generated images that the ambient diffusion model learned, and they look pretty good. They're not, for sure, as good as a model trained on clean data. So there's a trade-off here on training on corrupted data versus training on clean. But we say that it gets reasonable performance despite the initial training data being very bad. And here is a quantitative comparison here. As you're adding more and more corruption in the training data, you can see that ambient diffusion kind of stays reasonable but deteriorates in performance. But of course, if you just try to train a normal diffusion on corrupted data, you're going to get a terrible generator that produces corrupted data, right? So it's a reasonable mitigation that also gives you the benefit of preventing memorization when you're fine-tuning. So I'm running out of time, so let me just quickly jump to okay, I guess just for fun, very quickly, I wanted to teach stable diffusion myself. So I wanted to say an image of Alex, right? And as we said, the model doesn't know me. So how do we train the model to learn me? You fix the model and you only do gradient descent in this vector. So you say, this is a vector, I'm going to do gradient descent. So when you say an image of Alex, it produces something that's close to this target image. So we're doing gradient descent over the embedding of Alex so that the generated image minus the target, this is the target, is minimized. So we learn a token that corresponds to me, okay? And so we create a pseudo word, so to speak. So after you create this new vector that corresponds to me, you can say Alex playing with cute dogs, for example, and get like this type of results that it's always me. Now, one funny thing is once you do this naively, I have become everyone, okay? So if you say Alex is playing with Barack Obama, it will still be me and me. But somebody, it will look like Barack Obama a little bit, but it will still be me. So here is, for example, Alex as Agent Smith in the Matrix movie, and I am everyone. So this is actually an open problem as far as I know. How do you keep Stable Diffusion, keep its other identities, but still introduce a new identity? So, or introduce two new identities that are not fighting with each other. So there's a lot of interesting work when you're trying to teach these models new concepts, but without destroying what they already know. So there's a lot of fun research to be done there. And I will wrap it up quickly. So as I said, I spoke first about data comp, the creation of the data set, and then I spoke about teaching foundation models new tricks. I told you about how you can do in-painting by getting a better diffusion in the latent space. I spoke a little bit about how to customize foundation models on new data sets, and how this can be done even if the new data set has corrupted data with this trick of ambient diffusion. You can look at the papers, of course, or ask me for more information. I'll be glad to chat more. And there's many, many questions. For example, uncertainty quantification is a huge problem in inverse problems. Obviously, reducing the training set memorization is something I spoke about. And also personalizing foundation models is an extremely important problem for a number of reasons that I'm listing here. So I think there's a wide space to do interesting research here, including training foundation models for new domains, as people mentioned, like, for example, for MRI and proteins. We're working on those in IFML, but there's many, many other domains. So it's, I think, extremely interesting. So I'll wrap it up and take questions. Thank you very much.
Thank you so much for the really wonderful talk. Do we have any questions from the audience? Arya clapping. I have one quick question. Like I have a bunch of questions, but since we are out of time, I'll like very quickly ask. So for the patch fixing example, if the patches that were removed, like if they are different, like you're assuming like it's the same patch that is being removed from all the images that you see.
No,
So the
no,
A
no,
is
no.
the same. No, the A is not the same for all the images.
No, it's no. Okay, good, great point. No, absolutely not. A is random. Every time you I have a training. Let me see. When I have an image in the training set, like this,
yeah,
these are random. So the training set came to me, right? So somebody before they gave me the data set, they took images, they randomly placed pixels and deleted them, but they didn't delete the same pixels in all the images.
Okay, I just know it's a subsampled identity, but it's like according to some distribution.
It's a constant distribution, it's IID.
Okay.
Otherwise, there's no way I can learn, first of all. And then when I'm corrupting, I'm also corrupting every image with a random A hat.
Yeah.
So this is key, exactly.
Okay. And also like when you're training or fine-tuning with corrupted images, so if you have like you don't have any corruption budget, right? Like you are just like corrupting like really badly. But if you have some corruption budget that I don't really want to like corrupt a whole lot, but I want the images to look kind of similar to the original images.
Yeah.
So like somewhat like constructing adversarial examples.
Yeah.
Right. So is there something that is known in that kind of a domain?
Yeah, that's a key question. I can tell you a few things that I know. In theory, for some types of corruptions, there is no loss in quality. So in theory, if you can corrupt, as I said, for example, given X, I can choose a vector, A, Gaussian IID, and you give me A transpose X. So you give me a scalar, and you give me A also. So I observe only a single pixel, and I can still provably perfectly learn a distribution of X. The proof of that is in our ambient GAN paper.
Okay.
So there is no inherent trade-off in quality that comes from fewer observations or more corruptions. It depends on the nature of the distribution and the nature of corruptions. But in some cases, you may have no penalty in theory. So even the theory of this is not fully understood. So it's not as obvious. There seems to be a trade-off, but the trade-off is non-trivial.